Two golden records are currently drifting through the emptiness of interstellar space, each one carrying the sounds of Earth, whale songs, human greetings in 55 languages, a beating human heart, 90 minutes of music spanning cultures and centuries, launched in 1977 with a genuinely serious purpose, the faint, hopeful possibility that somewhere out there, someone might actually find them. And scientists have now actually calculated how long these two spacecraft could realistically keep drifting before that ever happens. And the number they came back with genuinely stretches the limits of human imagination. So in this video, I want to walk you through exactly what the Voyager golden records actually are, why they were put on these spacecraft in the first place, what the real, honest odds of an alien actually finding them look like, and what scientists now believe could happen to these two tiny human-made objects across timescales so enormous they make almost every other number in astronomy feel small. By comparison, so let's start with understanding exactly what we're actually talking about, because a lot of people have heard the general idea of a message to aliens without understanding the actual details behind it. Voyager 1 and Voyager 2 launched from Earth in 1977, originally built with a fairly focused, practical mission, flying past Jupiter and Saturn to study those planets and their moons up close for the very first time, and Voyager 2 went on to also fly past Uranus and Neptune, becoming the only spacecraft in history to ever visit either of those two outer planets, and both missions succeeded spectacularly, returning genuinely groundbreaking science and images that reshaped our understanding of the outer solar system. But bolted onto each spacecraft was something considerably more poetic than a scientific instrument, a gold-plated copper phonograph record, and the story of how that record actually came together is genuinely worth understanding, because it wasn't a casual afterthought. NASA assembled a small committee specifically to decide what exactly should go on it, chaired by the astronomer Carl Sagan, working alongside a team that included several colleagues from Cornell University. And this committee spent real time carefully deliberating over exactly what would best represent humanity and Earth to any potential audience light years away. And what they ultimately settled on was genuinely comprehensive. More than 100 images depicting human life, human anatomy, our cities, our landscapes, our various forms of daily existence, spoken greetings record, in 55 different human languages, plus one additional greeting from humpback whales, natural sounds of Earth itself, wind, thunder, birdsong, ocean waves, roughly 90 minutes of music carefully selected from a huge range of cultures and historical eras, everything from Bach to Chuck Berry to traditional music from cultures across the globe, and a written, formal message from the President of the United States at the time. And the record's cover itself was engraved with a set of symbolic instructions, essentially a diagram explaining how to actually play it, along with a stylized map showing Earth's location relative to a set of nearby pulsars. Cosmic lighthouses whose extremely precise, regular timing could theoretically help any sufficiently advanced civilization calculate exactly where in the galaxy this record actually came from. And I think it's worth pausing here to actually address the honest, complete truth about why this record was created in the first place, because the popular, simplified version of this story tends to frame it as a genuine, serious attempt to actually contact aliens when the people who actually built it understood their own project in a considerably more modest, more honest way. Carl Sagan himself was genuinely direct and clear about this specific point, stating plainly that the record would only ever actually be played if advanced, spacefaring civilizations happen to exist somewhere out there in interstellar space, specifically positioned to find it. And he described the entire act of sending it not as a realistic, practical attempt at making contact, but as a statement about humanity itself, about who we are and what we chose to say about ourselves, sent outward regardless of whether anyone would ever actually receive it. And I think that distinction genuinely matters because it reframes this entire story in a way that's honestly more moving than the simplified alien contact version. This was never primarily about reaching aliens. It was about humanity leaving behind a genuine, carefully considered artifact of itself. A kind of message in a bottle tossed into the largest possible ocean with full, honest awareness of just how unlikely it was that anyone would ever actually find it. And now let's actually talk about those odds, because I want to walk through exactly why the chance of an alien civilization ever actually encountering either Voyager spacecraft is, by any reasonable measure, genuinely close to zero, and understanding why requires actually grasping just how mind-bendingly empty interstellar space really is. Both Voyager spacecraft are traveling on trajectories that were never actually aimed at any specific star at all. Their paths were determined by the specific planetary flybys their missions required. Jupiter, Saturn, and for Voyager 2, Uranus and Neptune too, meaning wherever they happen to be heading now is essentially an incidental byproduct of that original planetary mission, rather than a deliberately chosen path toward any particular destination, and the actual numbers involved in their eventual extremely distant stellar encounters genuinely illustrate just how vast the emptiness between stars truly is. Voyager 1 is on a trajectory that will bring it within about 1.6 light years of a star called Gliese 445, sometime around 40,000 years from now. And Voyager 2 is expected to pass within roughly 1.7 light years of a star called Ross 248 on a similar multi-thousand-year timescale, and I want you to actually sit with what that specific distance, 1.6 light years, genuinely means. Because the word near in this context needs to be understood very carefully. 1.6 light years works out to roughly 15 trillion kilometers. And for comparison, that's actually further than the distance separating our own sun from Proxima Centauri, the nearest star to our entire solar system, meaning even the closest stellar encounter either Voyager spacecraft will ever experience across tens of thousands of years of continued travel doesn't come anywhere close to what you or I would naturally think of as a visit. The spacecraft won't enter that star's planetary system, it won't pass. Anything resembling close to any potential planets that might exist there, it will simply glide silently through the darkness, far outside any plausible range at which the golden record could ever realistically be noticed by anyone, even if intelligent, technologically capable life happened to exist in that exact system at that exact moment. And I think that specific detail genuinely reframes the entire alien contact framing. This topic often gets covered with online. This isn't actually stack all 5 of those individually improbable steps together, one on top of the other, you end up with a genuinely, vanishingly small overall probability. And I think that's exactly why researchers studying this question consistently describe the odds using words like infinitesimally small or close to zero by any reasonable measure. And I want to be genuinely clear that none of this means creating and launching the golden record was in any way a wasted, pointless effort. Quite the opposite, actually. And I think it's worth explaining exactly why that's true, because the value of this project was never actually contingent on it succeeding at making contact. The golden record has already accomplished something genuinely meaningful right here on Earth. It forced an entire committee of scientists to sit down and seriously grapple with an extraordinarily difficult question. What would we actually want to say about ourselves if we genuinely only had one chance to say it? Distilled onto a single small disc, and that exercise itself, choosing which music truly represents humanity, which images capture something genuine about who we are, produced something that continues to resonate with people here on our own planet nearly 50 years later. Inspiring books, documentaries, mirror held up to humanity itself, and the fact that it happens to be drifting through space rather than sitting in a museum simply adds a genuinely poetic, almost unbearably vast scale to that same basic human act of self-reflection. And now, let's get into the part of this story that genuinely connects to your video's original question: what actually happens to these 2 spacecraft over truly enormous stretches of time? Because this is where the science has recently produced some genuinely mind-bending, almost surreal answers. Researchers Jonathan Oberg and a colleague conducted a detailed study specifically examining exactly what might happen to the Voyager spacecraft and their golden records across cosmic timescales, using updated, extraordinarily precise data from the European Space Agency's Gaia mission, a spacecraft specifically designed to map the positions and movements of more than 1 billion stars with remarkable accuracy. And by combining that precise stellar mapping data with detailed projections of the Voyager's own trajectories, the researchers modeled out the spacecraft's probable future. And their findings genuinely stretch forward across a timescale that's honestly difficult to even conceptualize. Their forecast extends not just beyond the eventual expected extinction of humanity itself, but beyond the predicted collision between our own Milky Way galaxy, and 10 days before the rest of the world even knew a genuine interstellar object was heading toward us, one telescope had already photographed it, quietly, without realizing what it had found. That telescope is the Vera C. Rubin Observatory, perched high at the summit of Cerro Pachon in the rugged Chilean Andes, and the story of how it quietly beat every other instrument on the planet to the discovery of humanity's 3rd confirmed visitor from another star system is one of the strangest cases of cosmic timing in modern astronomy. It's a story about a machine so powerful it accidentally photographed history before history had officially happened, and about a determined team of scientists who had to go back months later and dig carefully through the archives to realize what they'd actually caught on camera. Here's exactly how it all unfolded, step by step. On July 1st, 2025, the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built specifically to hunt for objects that might one day threaten Earth, flagged a fast-moving point of light near Rio Hurtado, Chile. Within a single day, The International Astronomical Union's Minor Planet Center had confirmed what many astronomers already suspected, the moment they carefully plotted its unusual trajectory. This wasn't a normal asteroid or comet native to our own solar system. It was moving on a hyperbolic path, arriving from interstellar space, and it would become known as 3I Atlas, the third confirmed interstellar object in recorded human history, following Oumuamua in 2017 and Borisov in 2019. Telescopes around the world scrambled to turn their instruments toward it. But months later, a team of astronomers led by Colin Orion Chandler decided to check something. The Vera Rubin Observatory, one of the most anticipated telescopes ever built, had been in the middle of its commissioning phase throughout 2025, a critical testing period during which engineers and scientists fine-tune the instruments, calibrate the cameras, and validate that everything is working exactly as designed before the observatory's real, decade-long survey officially begins. During that commissioning phase, Rubin had been taking test images of the sky, essentially practicing, pointing its enormous camera at various patches of space to make sure everything functioned correctly. So the team went digging, they pulled up Rubin's commissioning data, and searched for any frame that happened to overlap with the patch of sky where 3I Atlas would have been, going back before its official July 1st discovery date. And there it was. Not once, not twice. Rubin had serendipitously captured 3I Atlas 9 separate times between June 21st and July 2nd, 2025, up to 10 days, before the Atlas survey ever flagged it, and before anyone on Earth knew an interstellar visitor was even in our skies. The observatory had photographed the discovery of the decade purely by accident, simply because it happened to be testing its camera on the right patch of sky at the right moment, completely unaware of what was drifting through its field of view. To put that in perspective, you have to understand just how staggering the Vera Rubin Observatory actually is as a piece of engineering. It houses an 8.4-meter telescope, paired with the largest camera ever built for astrophysics, a digital sensor roughly the size of a small car, capable of capturing images so detailed and so wide that a single photograph can contain 10 million galaxies. It was originally conceived back in the mid-1990s, under a very different name, the Dark Matter Telescope, before evolving into what it is today, the centerpiece of the Legacy Survey of Space and Time, an ambitious 10-year project designed to photograph the entire visible southern sky over and over again, cataloging every single change, every flicker, every faint moving object, building what will eventually become the most complete motion picture of the universe ever assembled. When Rubin released its first debut images back in June of 2025, the results were staggering even by the standards of modern astronomy. In just a few nights of test observations, the observatory had already revealed more than 10 million previously unseen galaxies clustered around the Virgo cluster, along with roughly 2,000 previously undiscovered asteroids, spotted almost as an afterthought during what was supposed to be routine calibration. This is a telescope so sensitive that it can see roughly 100 times fainter than most other sky surveys currently in operation, which is precisely why, months later, when astronomers turned back to the archives, hunting for any trace of 3I Atlas before its official discovery, Rubin's data delivered. It's worth understanding just how long this project has been in the making, because it puts the observatory's precocious accidental discovery in a much bigger context. The idea for what eventually became Rubin Observatory dates all the way back to the mid-1990s, when it was first conceived under a much more modest name, the Dark Matter Telescope, a project aimed at mapping the invisible scaffolding of dark matter that holds galaxies together across the universe. Over the following 3 decades, that original concept grew into something far more ambitious, a facility funded jointly by the National Science Foundation and the Department of Energy, built specifically to conduct the Legacy Survey of Space and Time, a 10-year campaign to photograph the entire visible southern sky, over and over again, building up what will eventually become the single most detailed motion picture ever made of the changing universe. The telescope itself was eventually named after Vera Rubin, the astronomer whose painstaking observations of galaxy rotation in the 1970s provided some of the first definitive evidence that dark matter exists at all, a fitting namesake for an instrument built to hunt for exactly the kind of invisible, hard-to-detect phenomena she spent her career chasing. The scientific goals behind Rubin Observatory extend far beyond hunting for interstellar objects, and it's worth appreciating the scale of ambition here, because it explains why the telescope is quite this powerful. Astronomers are hoping the survey will help resolve some of the deepest open questions in modern physics, the true nature of dark energy, the mysterious force apparently accelerating the expansion of the universe, and the distribution of dark matter itself, mapped out across billions of galaxies with a level of precision no previous survey has come close to achieving. Rubin has already begun contributing to that broader mission, producing what researchers have described as one of the most comprehensive 3-dimensional maps of the universe ever created, built from early survey data collected during its opening months of operation. Alongside that cosmological work, The telescope is expected to be exceptionally well positioned to catch rare, fleeting astronomical events that other surveys simply miss, failed supernovas, in which a massive star seems to just vanish without the expected explosive flash, and fast radio bursts, along with a huge range of other transient phenomena that only reveal themselves for a brief moment before fading from view. Interstellar objects, it turns out, are simply one more entry on that very long list of things this telescope was built to catch, just one that happens to be getting an enormous amount of public attention right now, thanks to 3i Atlas. But finding those images wasn't as simple as just pulling up a folder and scrolling through. Rubin's automated pipeline for identifying and tracking fast-moving solar system objects wasn't even operational yet during the commissioning period. The software specifically designed to flag things like asteroids and comets zipping across the frame hadn't been switched on. So Chandler's team had to build custom analysis techniques essentially from scratch, manually combing through the commissioning images, extracting astrometric measurements, precise position data, along with photometry, which is essentially a measurement of brightness over time in order to properly characterize what they'd found. Despite the challenges, the results were remarkable. Using this recovered data, the team was able to independently determine 3i Atlas's orbit, study the structure of its nucleus, and, most impressively, capture the earliest high-resolution evidence yet of the comet's activity, clearly showing the presence of its fuzzy coma, the cloud of gas and dust that surrounds an active comet's icy core, in images taken well before any other observatory on Earth had turned its attention toward the object, which raises an almost bittersweet question that the researchers themselves acknowledged. If Rubin's science validation survey had simply started a little bit sooner, and if its automated detection pipeline had already been up and running, this brand new, barely finished observatory might have been the very first telescope in human history to officially discover 3i Atlas. Not the Atlas survey network it was named after, not any of the other observatories that scrambled to observe it after the fact, but Rubin itself, almost by pure coincidence, simply because it happened to be testing its instruments on precisely the right patch of sky during precisely the right 10-day window. Astronomers joked, somewhat affectionately, that they'd be grumbling about hosting a nearly year-long visit from an interstellar guest, but in truth, the scientific community has been thrilled. 3i Atlas turned into one of the most thoroughly observed objects in the history of solar system astronomy, and Rubin's accidental recovery images added an entirely new, unexpected layer to that story. Proof that the most powerful new eye ever pointed at the sky had, in a sense, already been watching before we even knew there was something worth watching for. The 3i Atlas precovery wasn't the only headline-grabbing discovery to come out of Rubin's commissioning and early survey period either, and it's worth pausing on a couple of the others, because together they paint a picture of just how relentlessly productive this telescope has already been, even before its main 10-year survey truly hit its stride. In January of 2026, a team led by University of Washington astronomers, sifting through early Rubin data, identified an asteroid roughly 0.4 of a mile across that turned out to be the fastest spinning asteroid of its size ever recorded, completing a full rotation in under 2 minutes. A rock roughly the size of 8 football fields, tumbling through space so quickly it would tear itself apart if it were spinning even a little faster. That discovery, published as the first peer-reviewed paper to use data from Rubin's LSST camera, was itself found almost by accident, buried inside pre-survey observations, never originally intended to hunt for anything so specific. And in the observatory's very first weeks of operation, during what astronomers called an early optimization survey, Rubin had already logged more than 11,000 never-before-seen asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects drifting in the frozen outer reaches of the solar system, all discovered in roughly a month and a half of observing. Set against that backdrop, the retroactive discovery of 3i Atlas in the archives almost feels less like an isolated fluke and more like a preview of the telescope's baseline operating mode. Astonishing discoveries showing up practically every time anyone bothers to look closely at the data. Now here's where the story gets even more interesting, because this episode wasn't really about one lucky coincidence. It was a preview of exactly what Rubin Observatory was built to do on a scale that's about to become almost impossible to comprehend.